All right. Well, it's 3 o'clock. We'll go ahead and get started, everybody. Good afternoon. So I'm Jess McCauley. I work for Prince William Soil and Water Conservation District. And I'm excited to introduce Dan Schwartz, who is his presentation on building healthy soils. So we'll do questions at the end during a 5-minute Q&A. So Dan Schwartz holds a bachelor's and a master's degree in environmental science from the University of Maryland and Virginia Tech. Since 2003, Dan has worked as a soil scientist for the Northern Virginia Soil and Water Conservation District. His first years with the district were spent outdoors doing field work to update the Fairfax County soils map. Since then, his work responsibilities have broadened to include outreach and education, technical consultation to county agencies, soil and stormwater research, erosion and drainage assistance to landowners, and implementation of the district's residential grant programs. So here is Dan Schwartz presenting Building Healthy Soils.
Thank you. Thank you, Jessica.
Thank you.
Thank you, everybody. It's nice to be here. Nice to be here in person after a couple of years spent on Zoom. I think I'm probably preaching to the choir a little bit. I see some familiar faces. Definitely the choir. Obviously, you're here on a weekend, spending your whole day, your whole Saturday learning about native plants. So you probably have a little appreciation for soil to begin with, but I'm hoping this presentation will fill in some of the gaps in understanding and maybe, make you even appreciate it just a little bit more. I apologize, I'm gonna have to kind of stay over here because I'm advancing the slides on the keyboard, but I'll try and walk around. If anybody can't hear me though, just raise your hand and I will do my best to project. So, as plant people, it's fairly obvious what grows on the surface. When we're getting good plant growth, we can see it. But really, you need to have healthy functioning soil, which means a really good soil ecosystem in order to get that good plant growth. And a lot of times it's a little hard to understand exactly what's happening below ground. Visual people, we can see things and understand things that are, apparent to our eyes. And even though a lot of the stuff that's going on in soil is literally just a few centimeters below the soles of our feet, it's just out of sight. It's just hidden below the top layers of vegetation and the soil itself. So we can't see it with our naked eye. And that makes it seem a little bit mysterious at times, but it doesn't necessarily have to be. So that's kind of what I'm going to present today is you can really get into the weeds when you get into soil. There's a lot of specific stuff you can look at: pH, nitrogen, nutrient balances, types of organisms that living in there. But generally, when we're talking about native plants, you want to recreate a soil that is similar to what would have been outside of these doors before all this development came in here. So you're not trying to create the perfect soil necessarily. What you're trying to create is a functioning soil that acts like a natural soil. So natural soil, when you get it built up and really healthy, it kind of reinforces itself. You'll see there's a lot of talk in this presentation about cycles. A lot of the cycles that occur in soil are naturally reinforcing. If you can get it started, it will kind of take care of itself after that point, with less and less management needed, less and less input needed from you, the grower. So what happens above ground, all that good plant growth that we see, is really impossible without these guys underground. You think about basically half and sometimes more of the plant itself exists underground. We don't see the root system, but we know it's there. For a large tree, that root system is snaking out dozens and dozens and dozens of feet away from the trunk. And we really need to create the right environment for those roots in order to get the good plant growth that we can see above ground: the roots, the shoots, the flowers, and all the stuff that we are able to see. So we're going to talk a lot today about soil ecology, because it's really the ecology. It's these little guys, these little critters down below that we can't see when we're standing on the surface. And in many cases, we can't see even if we're looking in the soil, because most of this stuff is microscopic. But it's these guys that really power the cycles that give us healthy soil and therefore give us healthy plants as well, too. So let's start first with a little bit of a conceptual notion. What is soil? We'll talk about soil first, because I think people have a misconception about what soil actually is. So sort of in this grand general idea of what soil is, I think of it as the skin of the earth. We think of the earth existing in 3 general spheres of matter. We've got our hydrosphere, our lithosphere, and our atmosphere. What is the hydrosphere? That's all of our water, from the Atlantic Ocean down to our big bodies like Potomac River and the Chesapeake Bay, the Occoquan River, down to the little feeder streams that flow into those. And then even smaller than that, the pockets of groundwater in the soil, the little microscopic droplets of water vapor up in the air that create our clouds. All of that is the hydrosphere combined together. The lithosphere is our rock and the remnants of our rock. No matter where you are in the world, if you dig down deep enough, you are going to eventually hit solid rock. Around here, you only have to dig down about 3 or 4 feet in northern Prince William County. As probably some of you know, if you're gardeners here, you might have hit bedrock in your own backyard. It's pretty shallow around here. If you see those huge piles of spoil rock that they were digging up out of the I-66 widening, you'll know that you don't have to dig down very far to find rock around here. If you go to eastern Prince William County, around Woodbridge or Triangle or Dumfries, you might have to dig down 200, 300, 400 feet before you hit bedrock. So there's big changes from one spot to another. But eventually you will hit rock. And as that rock weathers in place, it breaks down into smaller pieces, sands and clays and stuff like that. That is our lithosphere. So the solid rock and the weathering products that break off of that rock. And then there's the atmosphere, which is pretty self-explanatory. It's the air that we're breathing right now. Where all 3 of those things combine together, that's where you get soil, right at the surface of the earth. And that's important to think about because we think about soil as a solid. But in reality, healthy soil, and I do put an emphasis on healthy because not all of our soil is healthy, so it's not all going to look like this. But a good healthy soil should have a dispersion of matter that's similar to this very simple pie chart up here. 50% by volume, solid material, 25% by volume, soil air, or what we call the soil's atmosphere, and 25% by volume, water. That's quite a bit different than most people probably think. We think of soil as a solid. This building is sitting on soil right now, so it's got some strength to it. But healthy soil is only half solids. The other half is open space that can be filled by air or water. Obviously, if you have a big rainstorm, soil is totally saturated. You can have a soil that's pretty much 50% water, 50% solids at that point. You have a really long drought, that air portion is going to get a lot higher. But throughout the year, this will be your rough average. And of course, this is a generalization, but your rough general average of what a healthy soil will be. If we look a little more in depth, we can break those soil solids down into their organic fraction. So organic matter is about 5% of the volume of soil, and mineral matter is about 45%. That is sort of your typical basic recipe for healthy topsoil right there. As you go down deeper in the soil, away from the surface, that organic constituency is going to get smaller and smaller. So even though soil solids may not make up as much of the soil as we might have thought, they still are important. So it's important to know what they are and what they do. So let's look at those 2 fractions, the mineral fraction and the organic fraction. Mineral fraction, when we're talking about soil minerals, we're talking basically about sand, silt, and clay, and also gravels, larger rocks. But generally speaking, a lot of times when we're doing a soil analysis, we actually sieve out those larger rocks and toss them, and we're just looking at the sand, silt, and clay. So really, most of the soil minerals are sand, silt, and clay. There's a lot of different types of sand, a lot of different types of silt, a lot of different types of clay. When we're talking about those kind of differences, we're talking about the chemical constituencies, like what's the magnesium and silicon and aluminum that makes up an individual atom of that sand, silt, or clay. We're not so concerned about that today. What we're looking is the general distinction between all sands, all silts, and all clays. And the general distinction is strictly one of size. So you can have the exact same chemical molecule. That it could be a sand, it could be a silt, it could be a clay, depending on its size. So the U.S. Department of Agriculture, and there are other groups that classify these things, but we usually use the USDA when we're talking about agriculture and plants. They classify sand as any mineral particle in the soil between 2 and 0.05 millimeters in diameter. Clay is any mineral particle between 0.05 and 0.002 millimeters, and then, silt. And then clay is any particle that is less than 0.002 millimeters. Those aren't necessarily numbers you have to remember by any means. They're kind of interesting if you want to use them in conversation, but it's not part of general knowledge that's really going to be helpful to you as planters, as growers, as horticulturalists. What's really important is that clay is a lot smaller than silt, which is a lot smaller than sand. What is 0.002 millimeters anyway? That's kind of an awkward division. That's 2 microns, so 2 millionths of a meter. So you need not just a microscope, but a really powerful microscope, like an electron microscope, in order to see an individual particle of clay. Silt is microscopic as well too. And sand kind of bridges the gap between microscopic and not. Larger particles of sand you can see with the naked eye. You've been to the beach, you can see those individual particles of sand under your toes or tracked back into your vacation house. But when you get down to the smaller particles, 0.05 millimeters, that's getting into the microscopic scale. Not very small microscopic, but you do need some magnification in order to see those small, very fine sands. I heard another presentation years ago, and I thought the analogy was really apt, but this master gardener was presenting about the relative sizes of sand, silt, and clay. So if you were to drive to a Commanders game, the stadium would be like a particle of sand, your car would be like a particle of silt, and the parking ticket on your windshield would be like a particle of clay. So that gives you a rough idea of how different these things can be, even though they all seem fairly small to us. So sand, silt, and clay, the difference between them is particle size. And we get down to the organic fraction. Remember, this is only 5% of the volume of the soil, so there's not a huge volume of soil taken up by organics, but they're very important. They consist, we can divide that fraction down further into living material. So the things like beetles or earthworms, the roots of the plants themselves, but especially the microscopic stuff like little microarthropods, where here we've got fungi, and here we have bacteria. If you were to take a teaspoon of healthy soil, about a gram's worth of healthy topsoil, you would find there'd be anywhere from about 100 million to 1 billion bacteria living inside. The fungi is a little different. They're multicellular. They generally take the form of these really fine little microscopic root hairs. They look like little tiny white twine working their way through the soil. Sometimes they bind upon themselves and a couple will combine together and you can actually see it with your eye. But for the most part, most of them are microscopic. If you could take each of those little root hairs in a teaspoon of topsoil and lay them end to end, they'd span anywhere from a couple yards in a farmer's field to anywhere from about 1 to 40 miles in a pine forest. Generally speaking, forests are dominated by fungi, forest soils, whereas prairie and agricultural soils and garden soils, ones that get a little more disturbance, are dominated by bacteria. But even regardless of that, we're talking hundreds of millions to billions of these organisms in any soil, regardless of where it is. And then the arthropods, some of them are macroscopic. Certainly you've seen beetles crawling through your yard, I'm sure, but a lot of those arthropods are little tiny microscopic insects. And you can find anywhere from a couple hundred to maybe up to 1,000 per square foot of soil as well, too. And that's not, there's other stuff living in the soil. There's roundworms, nematodes. There are protists and other sort of larger single-celled organisms, which you can find tens of thousands of per teaspoon. But these are the ones we'll concentrate on a little bit more today, but by no means are they the only living organisms in the soil. And of course, there's the dead organic matter. This is the organic detritus that gets added to the soil. Leaves are the great example here because we're mostly in a deciduous forest area here. But twigs, branches, dead trees when they fall, dead animals when they die, their carcass returns to the soil. Animal droppings, the manures from wildlife and from livestock all gets added to the soil as well too. So that's what we put in the dead organic matter category. Moving back quickly just to the mineral fraction, there's one important physical trait of the soil that I wanted to mention, and that's soil texture, which might be a term that you hear of a lot. Soil texture is very simply the percentage of sand, silt, and clay in your soil. This is disregarding any organic matter. So how do you measure soil texture is you take out the organic matter, you take out any mineral particles that are larger than sands, and you just look at your sand, silt, and clay. So those three percentages, sand, silt, and clay, will add up to 100. So you can have a really sandy soil and add a lot of organic matter to it. Still a really sandy soil because organic matter does not factor into texture. It's just sand, silt, and clay. When you say you've got a really clayey soil, you're sort of making an indirect analogy to the soil texture. That means that your texture is clay dominated. When you say you have a really sandy soil, it means your texture is sand dominated. And the texture is important because it really does affect the ability of the soil to retain water, nutrients, and it affects the infiltration rate of the soil, meaning the ability of the soil to take in water and oxygen. Now, these are very, very general, but they show you the patterns that we find in soil. So up in the top, we've got a very simplified, very general map of the water holding capacity of soil. To the right, nutrient holding capacity, and down below the infiltration capacity. if we were to have a magic mixing bar, like a DJ has, where they can, move sounds from one speaker to another. But this mixing bar allows us to change the texture of the soil. If we move it to the right, it starts adding clay. We go from 0% clay to 100% clay. Or if we move back to the left, it goes from 0% sand to 100% sand. How would that change in texture result in any differences in the changes in the water, nutrient holding capacity, and the infiltration capacity of the soil? Well, we start down at the bottom left of each of those graphs. We've got 0%, and let's say we start mixing our clay, and we start adding more and more clay until eventually we have a soil that's 100% clay, which you won't find around here. You also won't find a soil with 0% clay. You're always going to have a little bit of a mix of all three. But let's say theoretically it's possible. Well, that 0% clay soil really isn't going to be holding much water at all. But as we start adding more and more clay, clay has a very good ability to hold on to water. So the clay content increases and the water holding capacity of that soil increases as well. We do the opposite. We start mixing to the other side. We start adding in more and more sand and taking away the silts and clays until we eventually get a beach sand, pretty much close to 100% pure sand. What happens? As the sand content increases, the water holding capacity goes down. The same thing happens with our nutrient holding capacity. It's the same pattern. You start adding more and more clay to your soil, the nutrient holding capacity goes up. Clay has a great ability to cause nutrients, especially dissolved nutrients, to adhere to the surfaces of the clay. Same thing with water. As we start adding more sand, the sandier the soil gets, the less ability it has to retain and hold on to nutrients. But interestingly, that pattern reverses when it's the infiltration capacity. Again, infiltration is the general term for how easily oxygen, water, and other materials, but oxygen and water are what we care about, how easily those get from the surface and percolate down into the soil. Obviously, you add more sand, soil becomes more porous, water and oxygen quickly soak down into the soil, down to the root zones, down to all the microbes that live there. Start adding more clay, clay starts making the soil kind of dense feeling and sticky and gummy. It's hard for oxygen and water to penetrate down into a clayier soil. So the more clay you have, the less infiltration capacity. This is a problem though, because you want all three. You want good water holding capacity, good nutrient holding capacity, and good infiltration. I mean, a soil that has a lot of clay, great, you're going to hold a lot of water, but if the water can't get in there in the first place, it's not going to do you much good. Same thing with sandy soil. Got a lot of water entering through, but if it has no ability to hold that water, it's just going to leach right down to the groundwater without staying in the rooting zone long enough for your plants to access it. The other problem is texture can't be practically changed. If you are living with a sandy soil, you should just admit to the fact that you've got a sandy soil, and that's fine. There's things you can do. Can't really change the texture. I mean, theoretically you can. If you want to bring in 60 loads of clay with dump trucks, you could do that, but I don't think you are, and I don't recommend it. So generally, it's best just to resign yourself to the fact that you're stuck with the texture that you have. However, that's not the only soil solids there are in the soil. So we got sand, silt, and clay, and that's the texture, but then there's the organic matter as well, too. Even though that's only 5% of the soil, it has a lot of effect on the behavior and traits of the soil. So organic matter has a very large effect on the water retention, the nutrient tension, the infiltration, and something else, nutrient cycling as well, too. So all those things that are affected by texture are also affected by organic matter. And the nice thing is, while you can't change texture, you can fairly quickly change the amount of organic matter that's in your soil, entering your soil, and stored in your soil through various types of good soil management, good landscape management. Texture can't be changed, organic matter can. What does organic matter do? Well, what does organic matter do in the soil? It depends on the type. What is the role of dead organic matter? Dead organic matter is the base of the soil food web. So really, what I'm trying to hammer home in this presentation is that soil is an ecosystem and you want to take good care of it. The base of this ecosystem, the base of this food web that exists in the soil is organic matter, just as it is in our above ground ecosystem as well, too. Where does that organic matter come from? Generally from plants. So think of all those leaves that are falling off our deciduous trees during the fall, Think of all roots actually exude a lot of organic matter directly into the soil as well too. Think of, on a more domestic scale, the grass blades that you're cutting off. Where do they go? You can either bag them up or you can leave them on the soil. And if you leave them on the soil, they become part of the soil's organic matter. Then again, think of the trees, the branches that fall down during a heavy windstorm, or the trees that crack during an ice storm. They land on the soil surface, they become part of the soil organic matter too, as does dead organisms and their manures. So that's all getting added to the soil, and that is the base of the food system, the food web for all of those critters, those billions and billions of mostly microscopic critters that live in the soil. Now, the living organic matter, they're sort of the processors of the dead organic matter, or dead organic matter. So the dead organic matter is basically the soil food web that adds that organic carbon into the system, and the living organic matter that processes, that decomposes it. First step is the decomposers. These are basically your fungi and your bacteria. Their role, for the most part in soil, is to take that dead organic matter and start to decompose it, break it down. And they're not doing it for the good of the world. They're doing it for the good of themselves. That's their food. As they're decomposing it, that's how they eat. They basically digest things outside of their body. So they're adding, enzymes and stuff that are breaking this stuff down, and that releases energy that they can use, in organic carbon that they can use to reproduce and make new forms of themselves, new bacteria, new fungi. We also have the shredders. And the shredders are exactly like they sound. A lot of them are the little arthropods, little insects that live in the soil. They take big pieces of organic matter, maybe a twig or a leaf that's fallen, and they shred it into little pieces. And again, they're not doing this just for the good of the world. They're doing it because it's their food source. Some of them eat that organic matter directly. A lot of them actually graze on the bacteria or fungi that are living on that organic matter. But what they end up doing during their feeding processes is they shred that big organic matter, that big leaf, into little pieces of leaf. And if many of you are composters, you get faster decomposition in your compost pile when you shred stuff before you add it. Same thing happens when the shredders. When they're shredding the organic matter that gets added to the soil, they're putting it into smaller pieces that has more surface area that is then more easily attacked and decomposed by the fungi and the bacteria. So they're basically prepping this organic matter to put it into a state where it's easy for those smaller guys, those microscopic fungi and bacteria, to break it down. And then I'm kind of giving short shrift to the rest of the soil food web. It's very important, but we're not going to get into as much detail. But I would put the rest of the soil food web today in terms of liberating nutrients. And what does that mean? Well, the interesting part about the soil food web is that bacteria and fungi, bacteria especially, they like a food source that has about 24 parts carbon to 1 part nitrogen. And they actually increase the nitrogen in their body. So in their body, their carbon to nitrogen ratio is about 10 to 1, sometimes even a little bit less. These predators, the nematodes, larger animals, birds, the larger arthropods, even the amoebas and other single-celled organisms that prey and eat on that fungi and bacteria, they don't need as much nitrogen in their system. So when they eat those very nitrogen-rich fungi and bacteria, they actually pass a lot of nitrogen and other nutrients out through their waste. And if any of you have ever done farming or ever applied manure to your garden, you know that when you're adding manures or adding animal waste to a garden plot, you're adding a lot of nutrients there as well too. So what these guys do is they basically eat these really nitrogen-rich, lower-level critters in the soil food web, and they poop out soluble nitrogen and other materials as a result, because they don't need all that concentrated nutrient source. So by preying on them, they're basically creating soluble nutrients. And the trick with roots is they only have a very limited role in the soil. They take up two things. They take up oxygen and they take up water. So you're thinking, well, what about all the nutrients? Well, they take those up too, but they have to be dissolved in the water first. So these guys basically eat the lower level single-celled bacteria and multi-celled fungi and poop out a lot of that excess nitrogen and other nutrients that they had stored up in their body in a form that can then be dissolved in water. And that water is taken up by the plant roots. They're taking it up because they're thirsty, but they're also getting all those good dissolved nutrients in there as well too. So I put that under the banner of liberating nutrients. So I'm kind of, not going into too much detail. But there's one critter I want to go back to. It has a very important role. It's actually a branch of fungi, a family of fungi, if you will. And they have a very important role in collecting nutrients. And this is a picture of a pine seedling right here. Spruce. I've done my best. Spruce? Spruce? Okay, spruce seedling. I've done my best to try and draw out the roots of the seedling. And the rest of those roots there are something called mycorrhizae fungi. Mycorrhizae fungi are a type of fungi that will invade the root. It seems like they're infecting it, but what they're actually doing is they do grow sometimes inside the root cells, sometimes they wrap themselves around the root cells, and then they send their little fungal root hairs out into the rest of the soil. What that does is it effectively extends the reach of the plant's rooting zone, rooting interface. Those fungal root hairs work their way out in the soil where they contact soluble phosphorus and nutrients and water, and they take that material and they give it to the plant, and the plant gives them carbohydrates, food basically, that it makes through photosynthesis. So the plant feeds the mycorrhizae then scavenge the soil for water and nutrients for the plant. So it's this great beneficial relationship, and I'd say most trees around here have to have some relationship with mycorrhizae to grow.
The conifers are really dependent on them. The others do much better if they've got them.
Gotcha.
But they don't have to have them.
Okay.
And the way it says it's spruces, it's nitrogen fixer. It's in the nodules in it.
Ah, okay. Gotcha. Let's go back to our textural effects. Well, what we've done is we can add a lot of good organic matter to our soil, feed that soil food web, which will then decompose that organic matter and put it into a soluble and release nutrients in a soluble form, which the plants can then take up. We've kind of negated the negative effects that texture has on our nutrient holding capacity. So let's say you have a really sandy soil that doesn't hold nutrients very well. Well, the solution is really to add more organic matter, because as you add organic matter, you're getting that nutrient cycle really kicked into high gear as a result of feeding and stimulating the soil food web. And they start releasing nutrients for you from within the soil itself. So that becomes your nutrient source for the soil. So even if it's still a sandy soil, well, now you've got a good nutrient source and you can grow things on it as long as you've got that soil food web in pretty good shape. So add organic matter. That'll help you to shave off the sort of the rough edges of having a soil that doesn't have a very good texture for holding on to nutrients and retaining them. What else does organic matter do? Create soil structure. Now, structure sounds like a very unimportant thing. It's how soil solids are arranged together, how they're glued together. But it actually is a very important thing once we start finding out what good structure or bad structure does or doesn't do. So soil will naturally clump into little aggregates that we call PEDs. So if you go to Virginia Tech, Virginia State, University of Maryland, any of the agriculture schools around here, you'll see that the soil scientists are actually, their official title is pedologists. So they're people who study clumps of soil, basically. These are actual soil beds. They come in a variety of different shapes and sizes. What you like to see is that granular soil, and you typically find that in your topsoil. Oftentimes, if you dig down, you get into blocky soil, which is basically the same shape as granular soil, just a little bit bigger. Fortunately, what we do find a lot of in urban areas is plainy soil, which is often what happens when a nice, well-structured soil gets compacted by people, by machinery, by construction. And these two, massive and single grain, these are basically what happens when you have no structure. So if you go to a beach, that's single grain. Basically, every single grain of soil just doesn't adhere to any other grain. So it's just loose individual grains of sand, silt, and clay. In the beach case, it would be all sand, but a single grain soil would have some silt and clay in there too. Massive means everything's just one big chunk. Everything adheres to everything else. You just have one huge, undifferentiated block of soil. And you don't want that either, for reasons we'll get into. The reasons that soil structure is important is that it creates channels within the soil, pores within the soil. So the soil clumps together into those granules, those blocks. There's a few other shapes there, but those are the two that we see most commonly around here. And between each ped and its neighboring ped, there's a macropore, meaning a fairly large pore that allows water or oxygen to pass through, often powered by the force of gravity. Gravity just pulls that stuff down. Within the PEDs, there are micropores, small pores that act sort of like capillaries or wicking. So, you know, if you take a dry paper towel and you dip it into a little bit of water, you see that water start to work its way up the paper towel. That's what those micropores do. They actually hold on to water for the long term. So as the water makes its way down through the macropores during a heavy rainstorm, it'll move pretty quickly, but some of it's going to get whipped up into those micropores, and those will hold on to it for a good long time. And actually, within the micropores and some of the medium-sized pores, the water is more attracted to the surfaces of sand, silt, and clay, and that attraction is stronger than the pull of gravity. So they stay in the soil even, you know, days after the storm is ended. This is really important because you can imagine this is going to have an effect on infiltration. You have a nice, well-structured soil, which means we've got nicely, tightly adhered heads, but big gaps between them and their neighboring beds. So nice big macropores between each bed and its neighbor on top and bottom. We have a rainstorm. That's going to be a very porous soil that will allow water to quickly percolate and infiltrate down into the soil and down into the rooting zone, get to the roots of the plants, be available to the roots of the plants and all those other critters that live in the soil. If we have a compacted urban soil, let's say it was that same soil, but we ran across it with a bunch of backhoes, walked across it with a marching band or whatever you do in urban areas. That same rainstorm comes, there are pores there, but they're tighter and they're smaller, and they just don't allow water in nearly as quickly. So what happens is we get a lot more water pooling on the surface. If it's a flat soil, if it's a slope soil, it's going to become stormwater runoff, which is bad on its own, but for our purposes, it's bad because we want that water to get down into the soil. If the water can't get in the soil, it's not going to get to the roots at all. And what is causing these beds to form? Well, a lot of it has to do with our bacteria and our fungi. So as they're breaking down organic matter, they are creating something called soil humus, which is basically what you're trying to create when you have a compost pile. Compost isn't exactly the same as humus, but it's very similar. It's a resistant breakdown product. So soil humus is basically the stuff that is really hard to break down. It's too hard for these guys to break down. They break down the easier to decompose stuff. Bacteria break down the really easy to decompose stuff like sugars and things like that. The fungi break down the harder stuff like cell walls, lignin, things like that. But there's still some really tough resistant material left behind after they're done feasting. That's the soil humus. And the soil humus is very attractive to water, and it helps to, it's sticky. It's one of the natural glues that helps soil to adhere to itself. Clay is another one, and clay is in soil naturally. But if you don't have a clay soil, you can still get really good texture. Really good structure if you have a lot of humus, because it's just one of those natural glues that causes the beds to start to clump up. In addition, there's a lot of different types of organic matter that are created as these guys are breaking down, you know, leaves and twigs and stuff that kind of give a waterproof coating, if you will, to some of the beds. Because the beds are great if they're sticking together, but if you get in your first rainstorm, all those beds just dissolve, and then all your pores are going to be clogged up. A lot of the breakdown products, the organic breakdown products these guys create as they're eating away at that organic matter, allows those beds to basically sit in water in a solid form. It kind of gives them a waterproof coating, for lack of a better term, that prevents them from just dissolving every time we have a rainstorm or snow melt or sleet. So they sort of create the sticky gels, the humus that causes the soil to clump up into beds, and also create a waterproofing that prevents those beds from dissolving every time they interact with rain. And then we've got some of our bigger critters. Earthworms are the ones we're most familiar with, but the roots of the plants themselves, I would put both of these, as well as other critters, into our burrower category. If all we had were the small things that were clumping everything together, well, that's great, but we just come up with one big clump of soil. We also need stuff to work its way through the soil to create those pore spaces, to actually create the holes or the channels that allow water and oxygen to get through. So we sort of have to have our natural glues to get the soil to clump. We have to have our burrowers to break up the soil into those individual beds separated by macropores. And that's something that the earthworms are particularly good at, but the roots of the plants as well too. Roots, the small living roots at the tips of plants, the active roots, not the big woody ones you see coming out of the trunk itself, but the small little tiny roots at the very ends of the branches of the rooting system are constantly growing and dying. And as they die, they decompose and they've created a new pore space. So these guys are constantly burrowing through the soil, creating macropores, which allow oxygen and water to move through quickly. So back to our textural diagrams. Now let's say we've got a lot of good organic matter that's being broken down by our fungi and our bacteria, creating those natural waterproof glues. And then of course, we've got a lot of fungi and bacteria, and they're releasing a lot of nutrients that's going to attract plant roots, and it's also going to attract our burrowing organisms like our earthworms. Create those pore spaces. So we've kind of negated the bad aspects of texture on the infiltration capacity. So we have a really clayey soil in this case that has a naturally low infiltration capacity. The answer is not to import a lot of sand. The answer rather is to load up that soil with some good organic matter to feed the soil food web, so that the microbes and critters and larger organisms that live in the soil will naturally start to create that good soil texture through their gluing and burrowing activities. Lastly, talk about water holding capacity. So again, this is sort of an ideal graph, if you will. We've got on the left, the vertical axis, the volume of water that can be held in soil, and on the horizontal axis, we have soil texture. So as we move from the left to the right, we're moving from a very sandy, gritty soil with very little clay through a nice mixed soil, a mix of sand, silt, and clay, which is called a loam, and then we move on to a very clay soil. So the soils are getting finer and finer and finer as we go to the right, and coarser and coarser and coarser, sandier as we get to the left. How does this affect the amount of water that can be held in soil at any one time? Well, the total amount of water that is held in soil is actually not that important to us. It's the amount of water that is available to plants. And we figured this number out by finding two other numbers and subtracting them from each other. The first number is the field capacity. And that's basically the capacity that the soil has to hold water about a day or two after a really heavy soaking rainstorm. So during that heavy soaking storm, the soil is going to be saturated, which means every single pore, macro and micro, is going to be full of water. But after a day or so, after the rain stops, the macro pores will be clear. They'll be full of oxygen again. The way I kind of think of this is if you get a dry sponge from a supermarket, open it up, let's say you stick it under your faucet, put that faucet on really low, just let it drip. Put the dry sponge under, hold it in your hand, faucet drips on top. For about the first minute or so, maybe 30 seconds, all the water that drips onto that sponge is going to be absorbed in the sponge. You can see the sponge start growing as it absorbs the water. And after about 30, 45 seconds or so, you'll start to see that drips start coming out of the bottom. That's when the sponge is at saturation. Turn off the faucet, meaning turning off the rainstorm. That sponge will still drip for another 5, 10, 15 seconds or so, and then it'll stop. When it stops, that's sort of analogous to field capacity. So the biggest pores have drained out and have dropped their water because in the big pores, the pull of gravity is stronger than the attraction of that water to the surfaces of sand, silt, clay. But all the other medium and small size pores, they hold on to that water more strongly than the pull of gravity. So there's still a lot of water in that soil, not quite as much in saturation, but that's what we consider to be the field capacity. That's basically the highest amount that's available to plants, because the water that's going through those macropores and being pulled down by gravity, that only stays in the soil for, maybe a couple minutes to an hour or so. It's just not there long enough for the roots to access it. But at field capacity, it's held in the soil and the roots do have access to it. However, that's not the end all be all. So the other soil water content we're concerned about is the wilting point, which is pretty self-explanatory. This is the level of water in soil where you start to see your plants visibly wilt. The wilting point changes though. In the sand, the wilting point is basically zero. Basically, any water that's held in sand is available to the plants. But as we start getting more clay, more silt, but especially more clay, what we'll find is that clay holds a lot of water, but it's greedy about it. It holds it very, very tightly. So they form these films around the surfaces of clay, and the attraction of clay to the water is very, very tight. So tight in cases that when a root comes by and tries to suck up that water, it doesn't have the suction force in order to do it. The clay holds it tighter than the plant root can suck it off. So as a result, the wilting point actually gets very high when we have a very clayey soil. So naturally, if you have a loam, that's probably the soil that generally has the most plant available water, which is the difference between these two parts, the distance between them. So it holds a lot of water, but doesn't hold it too tightly. Sand holds very little water, but holds it very loosely. So it's almost all available, but there's so little to begin with. There's just not much there at all. Clay holds the most, but it holds it so tightly that the more clay you get towards the extreme end, the less water is available to the plants. But what happens if you start adding humus? So that decomposed organic matter. Well, humus is a lot like clay in one way, in that just like clay, it can hold a lot of water per unit mass, even a little bit more than clay can. Where it differs from clay is that it holds that water fairly loosely. So the water that binds to humus is generally available to the plant. So if you add a lot of good organic matter, which eventually become humus, to your soil, regardless of the texture you began with, you almost always will increase plant available water significantly, because it boosts up the wilting point just a little, but it boosts up the plant available water significantly, regardless of your initial texture, whether it's sand, a loam, or a clay. So now back to our graphs. Add organic matter, get a good humus content in your soil, and you can kind of negate a lot of the negatives that come with a texture, very sandy or a very clayey texture that might limit the amount of water that you naturally have available to your plants. Go through the layering of soils a little bit too, so you can kind of understand what you're seeing as you dig a little deeper in your own yards. We've got our O horizon on top. O stands for organic. O is basically the loose litter on the surface of the soil. A lot of people don't think of that as soil, but we consider it to be part of soil. Where most people think of soil as starting is the A horizon. This is what we refer to as colloquially as topsoil. It's our first subsurface layer. It's very rich in organic material, and it's going to have that nice dark brown or black color because it's full of humus, and humus is dark brown or black. In Virginia, we're lucky to get 2 to 5 inches of A horizon. That's not a bad thing. That's just what naturally occurs in the climate that we have with the plants that naturally grow here. You go to the Midwest, you might get 18 or 24 inches of A horizon because those are natural prairie soils out there, and they tend to create thicker A horizon. Ours are more natural forest lands. We do have prairies here, of course, as well too, but because of our climate, this 2 to 5 inches is what we get. But that's plenty for what we're trying to grow around here, especially if you're trying to grow native plants. They're used to that thin A horizon. But the important thing is, even though it's only 2 or 5 inches thick, that's where most of the biological activity is happening, where most of the living roots are, most of your microbes are, where most of the nutrient cycling is occurring. So they're just the first couple inches of soil. And that's not to say that the rest of soil isn't important, but from a biological and plant health standpoint, this is probably the most important layer. The E horizon may or may not exist in your soil. I'd say you find them in less than half of the soils around here. E stands for exit. It's sort of the leached layer, the acid wash genes layer of the soil. There's a lot of organic matter breaking down in the A horizon. This creates a lot of organic acids. Those organic acids kind of strip the E horizon of a lot of the things that give soil color, clays and organics and iron oxides. They just sort of get acid washed out of the E horizon over decades and hundreds of years. What you're really looking at the E horizon is sort of the uncoated colors of sand, silt, and clay. Most sand, silt, and clay is gray. It's coatings of iron oxide and organic matter and other metal oxides that give soil its color. Speaking of color, we get into our B horizon. And I'd say again, from probably more than half of you in your soil, you'll probably go straight from A to B. But some people do have an E horizon. Sometimes this is a really clear one. You're usually not this clear. If you have an E horizon, it's probably only going to be about 2 or 5 inches in thickness as well too. So it's pretty thin. The B horizon, on the other hand, you can get 18 or 24 inches of B horizon around here. We have a type of climate that creates a lot of clay. Clay actually starts forming up in the A horizon, but as that soil is aging and weathering in place, every time it rains, water passes through the macropores, picks up a few of those little clay particles and deposits them deeper down in the soil in the B horizon. So over time, the B horizon actually gets thicker and thicker and thicker as clay is driven down deeper and deeper. You go to a place like the Amazon, you can get clay layers 5, 6, 7 feet thick in some cases. That's also where we find the most color. Clay itself is not necessarily colorful. It's the iron oxide coating on clay, which is colorful. But generally, where you get a lot of clay, you also get a lot of iron oxide. Technically speaking, iron oxide is a type of clay because, for the most part, it's less than 2 microns in size. We get to the sea horizon, which is our transition layer between the highly weathered soil above it and the unweathered bedrock down below. It usually has less clay, it starts feeling drier, grittier, sandier, looser, just because you're losing that clay content. So it doesn't have the ability to hold water like the clay in the B horizon does. It doesn't have that dense feeling to it. And then finally, you get your solid bedrock, your R horizon. Now, if you live in eastern Prince William County, eastern Fairfax, basically if you live east of Interstate 95, you're in the coastal plain, and you might have to go down, again, 200, 300, 400 feet before you hit bedrock. In that case, your soil didn't form from bedrock. It formed from bands of sediment that were washed in thousands to millions of years ago by the Potomac River, or in some cases, the Atlantic Ocean, back when that was a floodplain. So soil doesn't all form from bedrock. Some of it forms from deposited sediments that were washed or blown in. And that is the case in eastern Prince William County. So what does a healthy soil plant system look like? If you're digging through your soil and looking at all these layers, what does a really good soil look like? Well, you're going to have an A horizon with lots of organic matter, and if possible, granular structure as well too, because you've got your microbes, they're breaking down organic matter, releasing nutrients. As they're breaking down organic matter, they're creating soil humus. That humus, again, is pretty resistant. Humus can stay in the soil for 50, 150, 200 years before it finally fully breaks down. So as they're creating humus, they're creating basically a long-term storage of organic matter in your soil, and you're going to see that in the A horizon. Nice granular structure like this. Some people call it crumb structure. It's loose, it's light, it allows in lots and lots of air and oxygen and water very quickly because it's got all those good macropores between those little particles, those little heads of soil. And as the water passes down into the soil, because of that good granular crumb structure, it dissolves the nutrients that are being released as the organic matter decomposes. Because again, basically what you're doing in the soil food web is you're adding raw organic matter, leaves and twigs, getting it decomposed by all the critters there or eaten by other organisms. And in this process, soluble nutrients are released out into the soil, dissolved in the water, and that gets put into the roots. The roots take it up. That helps power a new growth for your plants. And the cycle continues because healthy plants will add more organic matter back into the soil, sort of boost the system, if you will. Help to keep that cycle going themselves, either through their leaf drops or through direct exudation of organic matter through the roots themselves. Now, the problem is we live in suburban urban areas around here, and that causes a lot of changes to the soils. And from a soil health perspective and plant health perspective, almost all of those changes are bad. So one of the big ones we see is compaction. Soil gets compacted underneath construction machinery, it gets compacted underneath people just walking. When it gets compacted, a lot of those good pore spaces are squeezed out. And a compacted soil may be 75% solid, it could be 80 or 90% solid in extreme cases. And this leaves less open channel space for soil air and soil water, which is bad for the plants, but it's also bad for the microbes that are powering that nutrient cycle. I like to call this compaction impervious light. It's not quite an impervious surface, but it's not all that far from it. A really compacted soil might absorb a little bit of water, but probably a small fraction of what it would have absorbed before it was compacted. This is a fairly typical scene you'll see in a newer subdivision. It'll be interesting to go back in 20 to 30 years to see what that tree looks like, because that tree is planted in some pretty compacted soil between the roadway and the sidewalk. And perhaps if the roots can find a little bit less density soil, maybe they can grow. But this could just become sort of like a large bonsai, if you will. When the soil is compacted, it becomes stronger as well too. And sometimes it's so compacted that it's too hard for the roots to burrow their way through. That's a bit of an extreme example, but it is possible. And if it's difficult for the roots to penetrate, the size of the tree is balanced by the size of the roots. If the roots are stunted, the tree is going to be stunted as well too. Okay. And this is a really good example of it. This is a picture from Casey Trees of Pennsylvania Avenue. I think these are all pin oaks.
These are all willow oaks.
Willow.
Actually, Casey Trees stole that picture from somebody else.
Okay. But they were all planted at the same time. They're all the same species, but look how much bigger these are than these over on the other side. And why is that? Well, these are sort of trapped between the roadway and the sidewalk. They just don't have very much loose soil to grow in. So their roots are very constricted because the soil under the roadway and the sidewalk is extremely compact, and it's unlikely that those roots are going to be able to penetrate through, or at least they're going to have a really hard time to do it. Whereas here, I wouldn't say this is great soil, but at least they have this 30 feet of loose soil between the sidewalk and the building where it grow. And you can see the difference. Otherwise, they're growing in the same conditions, same temperatures, same age, but you can really see the change.
Same cultivar.
Same cultivar, yeah. The only difference is available soil they have to grow. Another effect of urban soils is mixing. When soil gets developed, it gets graded and mixed around, sort of stirred up. This often causes a lot of the fertile topsoil to be dispersed. Developers do try and stockpile the topsoil in a big pile and spread it out later. It's still, some is always lost, and stockpiling itself will damage the topsoil a little bit. It's obviously best just to keep it. But in worst case scenarios, you have this nice structured soil, and afterwards everything is sort of mixed into this almost uniform melange. And the issue is, you know, you really need that concentration of organic matter, organic humus up at the top to power that soil nutrient cycle. And if it gets dispersed, if that 2 or 5 inches of topsoil gets mixed in the first 2 or 5 feet, that really degrades its ability to do that. So when you lose that topsoil, you also lose all those microbes and that healthy functioning soil food web that powers the nutrient cycle. So this kind of forces us to rethink of what soil is. Is it a mix? Is it the intersection of the hydrosphere, the lithosphere, and the atmosphere? Is it a mix of sand, silt, and clay? Yes, it is those things, but it is also a very rich and diverse ecosystem, very complex food web. It's a great recycler of materials, specifically organic materials. You kind of think of it as being sort of like the digestive tract of the world's stomach. What do? We eat our food, it goes into our stomach, and all the microbes and acids in there break it down so that usable energy, organic carbon, and nutrients are put into a form that we can actually digest and use for our motion. And that's basically what soil does on a worldwide scale for all of the raw organic matter that gets dropped on it, leaves, twigs, dead animals, manures. All those microbes, earthworms, burrowers, arthropods, they're sort of like the microbiome of the world, if you will. They take those materials and they degrade it, decompose it, and put it into a form where those nutrients are available to be put back into the plants. How do you keep that stomach happy? Feed it. Feed it good stuff. What does it eat? Does it eat fertilizer? No. Fertilizer is useful in many cases, but it's a vitamin. What it needs is organic matter. In most fertilizers, you're getting nitrogen, phosphorus, potassium. There are some fertilizers that contain organic carbon, but soil food, the microbes' food in the soil has to contain organic carbon. The food source is organic carbon. Nitrogen, phosphorus, potassium, again, fine, but that's a vitamin. We take our vitamins in the morning. I take a vitamin. I'm still hungry. I want my bacon and eggs. You know, that's food. That's what fills you up and gives you energy. The vitamins give you nutrients, and that's important, but it's not energy. It's not food. It's a supplement, if you will. Food is something like compost. That's organic matter. You make your compost in your backyard. You don't have to buy it from the store. There are some products that kind of bridge the gap between fertilizer and soil food. This would be things like manures or malorganite, which, if you know what malorganite is, it is also manure. It's treated in Milwaukee sewage sludge. This has a lot of organic matter. It's also pretty concentrated in nutrients as well, too. So you can kind of consider this to be both a fertilizer and a soil food source as well. But again, to be a food source, it's got to have that organic carbon. But you don't have to go buy stuff. You don't even have to make a compost pile. You can mow in your leaves instead of raking them up and having the blower truck come and suck them up off of the curb. Because that's a lot of good organic matter that could go down into your soil. It's also a lot less work for you if you mow them in rather than rake them. Another simple one, you can leave the grass blades on your lawn instead of bagging them and taking them away. Grass blades are a great source of nitrogen. You can be a little more proactive. This person is actually hiring somebody to come in and rake out what they call a top dressing of compost. They're going to have guys with the rakes come in and rake those piles into about 1/4 or 1/2 inch blanket of compost that covers everything. Thin enough not to bury the grass, thick enough that that organic matter is going to be incorporated by earthworms and other burrowers into the soil and really enrich the soil with good degraded organic carbon. But really the simplest way to feed your soil, plant. Plant and plant densely, because again, growing plants are adding organic matter as they, die back and go into dormancy in the winter. All those leaves fall onto your soil. But even when they're growing, they are adding organic matter because they're pumping it out through their roots, because they're trying to goose that soil food system, because they have a lot of benefits from a lot of bacteria and fungi and stuff living in the soil. They're getting the nutrients. So they're actually feeding those microbes in order to get that nutrient cycle up and running. Plant, and as much as possible, keep the plant residues on site. Now, those of you who really like a nice, clean looking landscape like this homeowner might, maybe what you do is you take your clippings and you put them in a compost pile. So they're put away, but then once that's composted, you can spread that compost back onto planting bed. So in a way, it is keeping it on site. You're just sort of tucking it away for a little while. But the easy way to do it is just the stuff that normally would fall on the soil if you were out in the forest, keep that stuff falling onto your plant beds as well too. So the stuff that dies back, let it rot in place. And by doing that, you're feeding the soil food web, adding more organic matter, which is the base of the soil food web. This happens to feed those decomposers, which then are the food source for everything else in the food web as well too. So you're kicking the nutrient cycle into high gear as a result, because basically the soil food web is also a nutrient cycle as well too. It's recycling nutrients and putting them back in the usable forms that can be taken up by the plants. They're helping to create that nice healthy soil with good thick, very biologically active A horizon. By thick I mean maybe only 5 inches deep, but that's enough for us. You're creating a soil that will naturally over time help to decompact itself, because the more roots and organic matter you have living there, the more humus, which is low density, is getting added to the soil, the more roots and other burrowers are working their way through the soil, creating new macropores, so you can help to decompact it, compact the soil, make it loose, make it available to take in lots of air and water from the surface. And you're creating a resilient soil as well too. So remember, these things are natural cycles. You get that cycle up and running, it tends to reinforce itself. You get more of these guys in there, feeding good food into the soil food web, adding good organic matter, they're going to be strong. The soil food web is going to be strong. The nutrient cycle is going to be strong, and they reinforce themselves. That's not to say you won't have to do any management on it after that. But you look at a healthy soil. Who's managing healthy soils in a forest? Nobody. It just happens naturally because the organic matter is naturally being cycled through leaf fall and other deposition. And that's kind of what you're trying to recreate in your own yard. Get that natural cycle of organic matter returned back to the soil as best you can. So that's it. Hopefully we've got enough time for some Q&A. Is it all right? Yes.
Thinking about an area of the yard that is full of flag irises that a previous owner planted, and it is so dense. But like I'm thinking about how you're describing soil, and it's like full of roots, and I haven't stepped on it, and things have been falling on it, so it should be healthy, but like it's totally not. So how is I was trying to like get my head around what a healthy soil looks like. Does having like an invasive like that totally ruin the effects of good soil?
Not necessarily, but there are times when you need to have a little bit of a firmer hand, I would say. A lot of times if you have a decent enough soil, it's not great, but it's okay, things are growing. Sometimes the answer is just to keep planting on it and let it fix itself. If you have a really dense soil, really compacted soil to begin with where things aren't growing, it might be worthwhile going in there with something like a rototiller and some compost and really deep tilling in some material to sort of get things kick-started, if you will. And then planting densely with the stuff that you do want, which will grow up fast, crowd out the weeds, hopefully, and send their deep roots into the soil. And yeah, so it might be worthwhile in those cases where your soil is very marginal to begin with to, do like that homeowner was doing with the compost top dressing or something like that. In this case, I might actually even excavate down in. I usually say don't till the soil, leave it as is, but sometimes you have to. Yeah.
Sometimes you got to start over.
Sometimes you got to start over. Exactly.
I have a couple.
Yep.
So what is meant by well draining soil?
I guess that's in the eye of the beholder, because there certainly are plant types that like wet feet, but well draining for the purpose of this presentation means that basically water from the surface percolates quickly down into the soil. You don't see a lot of puddling on the surface. There are some areas where you do see puddling and it's natural. If you're in a floodplain and there's puddling on the surface, it's a floodplain. That's what it's supposed to do. But generally, if you're not in one of those really wet areas, you should see most normal sized storms, not our huge gully washers, but normal sized storms should soak down into the soil fairly quickly. You shouldn't really see puddles standing, a day or two after a rainstorm. So that's what well draining is in this
So,
case.
isn't there a test where you dig a hole and after 24 hours, you pour water in the hole, and after 24 hours, if it's completely empty, then that's considered well draining?
Yes, but that's a little more for deeper infiltration. I was thinking here mostly just surface stuff. And again, that deeper stuff that you're looking at, that might be natural groundwater that you're finding. Some soils just have groundwater very close to the surface, so that's useful to know because that probably tells you what you should be planting there, which is stuff that likes wet conditions. But there may not be all that much you can do about it from a management standpoint, unless you really want to bring in some big machinery, which again, we're trying to avoid. Yes.
What's the best way to create, efficiently and effectively increase soil velocity?
Well, organic matter is really kind of a broken wheel when it comes to that. But humus, if you can get humus forming in your soil, it's a very low density material. It's much less dense than sand, silt, or clay. And it has that, again, that ability to cause the soil to aggregate together. So that's probably the best way to do it. But really the best way to get humus growing in your soil is to have lots and lots of living roots in your soil. So that means to plant densely with deep-rooted vegetation, which is usually native vegetation. That's not to say, there are ornamentals that have plenty fine roots as well, but generally speaking, natives have deeper roots. Will exude a little more organic matter into the soil and help you build up that organic carbon storage. And it's not something you'll see in just a growing season. It's a slower process, but it will slowly build up. Sure.
I have one more quick one,
Okay.
sorry. At what horizon do we find groundwater?
It depends on where you are. So again, if you're in a floodplain, especially now that we're in February, groundwater might be right at the surface. So it'll be at the A horizon in some cases. So it's really more about your landscape position. If you're high up on the hilltop, you probably won't find any groundwater. If you're down low by a stream, you might find groundwater in any of those horizons. The closer you get to the stream, the higher that groundwater is going to be. So it's not so much the soil type as the landscape type.
Soil type is also important. You got rumsco.
Right. And so there are some soils that have thick clay layers, which are called a perched water table. The water can't percolate through that. But I'd say if you take a look, if you think you have high groundwater, take a look at the soil survey for your area to see what soil type you have mapped on your property, and it might answer a lot of the questions. Or if you're right next to a floodplain, that probably is your answer right there. And then you can chime in.
You're talking about decomposed shredders and all. You said they gave a ratio of 24:1. One I thought was carbon, that was missing 24. and
Nitrogen.
Organic carbon.
Carbon and nitrogen. So yeah, bacteria likes a food source that's about 24 parts carbon and 1 part nitrogen, or less. So 20-1 is fine too. If you feed them something that's a little higher than that, let's say like sawdust, which is probably 100-1, 100 parts carbon and 1 part nitrogen, very little nitrogen. The issue there is that the bacteria won't be getting the nitrogen they need from that food source. They'll break it down. Got carbon, they want that. But they'll have to look elsewhere for their nitrogen, and this can often put them into competition with the plants. And they'll start scouring around for nitrogen from other sources, which might be the nitrogen the plants want to take. So if you give them a good food source, which generally the natural droppings that fall on soil will have enough carbon, nitrogen. They get everything they need from that organic matter, and it doesn't put them into competition with other soil organisms or the plants themselves.
So the trees themselves that are dying and decomposing in the roots are high in carbon relative to nitrogen.
They can be, but it's
Those
those
are
are
nitrogen graft with either the wood chips or the larger woody matter. In fact, one of your best woody mulches is the stuff you get in your harvest truck straight out of the chip.
it'll be mostly the fungi that decomposes that. Fungi decomposes woody material, whereas bacteria decomposes the grass blades that fall, the juicier stuff. That's easy to decompose. That's why you find more of them in grasslands. There's not as much of that woody debris that you would find in the forest. And fungi has a different way. They can they can break down stuff that has a lot less nitrogen as well too.
People always leave bags of grass around by the curb, and I don't thought about not collecting those to use as mulch. Is that bad? I mean, does it mean that it might have chemicals on it from the lawn treatment?
It might, I wouldn't be too worried about it though. So, you know, even those chemicals, they are for the most part organic materials as well too, meaning they contain carbon. Doesn't mean they're all natural. As long as they're not there in such a high concentration that they'll kill the microbes that you have in your soil, chances are there's some species of microbes. There's thousands of species in the soil that we don't even know about. There'll be some species in there that'll be able to break down that pesticide or whatever it is into its constituent parts and make it safe, so to speak. So yeah, I think it would be fine.
Grass clippings are better for the annual grass, not as much for the woody perennials. The best advice is mulch like with like green annuals, you mulch with grass clippings and household pairings. Woody perennials, you mulch with wood. And I know you keep saying organic, dead organic matter. We have not record, we have 20 years worth of leaves on our property. We went from a 0A horizon to a 2-inch horizon.
There you go.
The next question was, you talked about the leached out soils. Is bringing that back up and getting at least a portion of it back up to mix in with the higher level soils. If you've got the ability to do so with enough organic matter to get mixed in with that, is that actually advisable or there?
No, I wouldn't. Basically, you've got a decently healthy soil. The best thing you can do is don't touch it, but don't till it, don't mix it. Because every time you go in and mix, you are in fact kind of physically destroying some of that good soil texture, so not texture, structure that you created. And that natural leaching that you find that happens. That's what soil is meant to do. And oftentimes there will be, some deep roots from some of these vegetation that will be able to get down in there and get some of that deeper nitrate or whatever else is leached out. But really what we see is that natural soils don't leach materials at a problematic level. It's when we add things like ammonium nitrate to our farms or to our grass, where we really dose a high level of soluble nutrients into the soil that we might have leaching problems that could be problematic for groundwater quality or surface water quality. So no, I wouldn't try and change the layering of the soil. Just let it do what it naturally does.
The only place I've seen the horizon around here is in long undisturbed forest soils.
Generally, we probably had a lot of e-horizon in the past, but a lot of it was destroyed by the plow. And this area is a big suburban area now, but for 250 years where it was pretty much all farmland, consistently farmed, and that tended to take that e-horizon and mix it into the A above and to the B below, and just kind of pulverize it. So it might reform again, give it another 200 years, maybe some of these lawn soils, if they just stay as are for a long time, you might see an e-horizon forming again. But yes, where